tell you kind of a little bit about how we take planets, baby pictures, but also why you should care, why this is the most interesting and important of the exoplanet detection methods that we have available to us. And I want to start with this plot, which sometimes turns people off, but I'm going to break it down for you. So obviously I haven't put any data on here yet, but this is going to be the planetary landscape. It's what we call a log-log plot, and I'll tell you in a few minutes why logarithmic scales are necessary in this case. But along the bottom here, you have the period of the planet's orbit in years. On a log scale means that every big tick here is a power of 10, so a multiple of 10. So 10 to the 0 means 1 year, right here, 10 years, 100 years, fractions of a year. This is directly translatable through Kepler's laws to the distance between the planet and the star. So a planet that has an orbital period of 1 year is about 1 astronomical unit, or 1 Earth-Sun distance away from its star. And then on the y-axis here, I have the mass of the planet in Earth masses. So again, 10 to the 0 is here, so this is about Earth's mass. 10 times, 100 times, 1,000 times, 10,000 times the mass of Earth. Okay, so I'm going to move forward in time here and tell you about the evolution of our understanding of the planets that exist in the universe. And on the bottom of the plot here, I'll put the year and then the number of known planets. And I actually want to start really far back in 1750. We know 6 planets. Can anyone tell me what they were? No astronomers are allowed to answer this. Jupiter, yeah, Jupiter, Mars, Saturn, not Neptune yet. Venus, yes, okay, so these are the 5 naked eye planets, plus Earth. We didn't know about ourselves as well. So here's where I want to take a brief digression to explain why I want this to be a log-log plot. So you see how nicely spaced these all are right here? If I put this on a linear scale, where every step along the axis is the same actual size, all of the terrestrial planets end up way down here, and then you get a bunch of blank space between those and Saturn and Jupiter. So log-log plots are really nice when you have things that span a very wide range of values, from fractions to hundreds of thousands. Okay, if we jump forward to 1785, this was the first time that a planet was discovered with a telescope, Uranus. And then, in one of my favorite sort of historical stories, we predicted the existence of Neptune with math. A French mathematician named Leverrier predicted the location of Neptune. I'm an American, so I am contractually obligated by my nationality to mention that Clyde Tombaugh discovered Pluto in 1930, even though it's not a planet. And I can talk about why later if you care. And then nothing happened for a very long time, until 1995. So I want you to put yourself in the mindset of people in 1994 and think, what do you think people thought about when someone said planet around another star? Where would the ideas come from? Can anyone think of anything? Anyone who was around? I'm sure some people in the audience were not around in 1994, but if you were, and I said, hey, what's a planet around another star look like? What would you have said in 1994? Like Earth, good. Sometimes we got slightly more creative than that. I'm pretty sure that's just an image of Mars from Star Trek The Next Generation. But the most creative that we got was maybe a planet around a very Earth-like planet around a binary star system. So, our conception of what planets looked like in 1994 was basically probably like our solar system. The very first planet that was discovered after this, 51 Pegasi b, right here, completely breaks that. It doesn't look anything like any of the planets in our solar system. It's closer than the orbit of Mercury to its host star, and it's almost as massive as Jupiter. That just like completely breaks everything that we understand about the planets in our solar system. So because I have a limited time, and I don't care about hot Jupiters, I'm not going to talk about these. But I want to jump way, way forward to today. I made this plot for you about an hour ago. So in 2022, these are the planets that we know about. I've colored them here according to the method that was used to detect them, where the planets that I study are these sort of reddish ones in the outer regions. We know of 5,044 confirmed planets now. So I want you to take 1 minute and talk to your neighbor and tell me about something that you either notice about this plot or a question that you have. And I'm going to elicit those in 1 minute. Go. Okay. Really nice and loud. Tell me something you observed about this, or a question that you have. Sorry. I guess astronomers, are allowed to ask a question if you're not an exoplanet astronomer. Good. Okay, there's a big white space here. So one of the takeaways is certainly that so far, one thing that people conclude about this sometimes is that there are no planets in that bottom right-hand corner. But this is purely selection effects. We have no reason to expect that there aren't planets in that bottom right-hand corner. It's just that we are most sensitive to the planets up here with most detection methods. So another way of saying this could also be that you'll notice that the solar system planets are at the very sort of boundary of what we know about now. So we're kind of just now reaching the point where we can detect real solar system analogs. With time, we are moving down and to the right in this plot as we improve the technologies. Any other observations? I'm sure you had them, but again, in the interest of time, let me tell you, yes, Jared Mills.
Why is directed music so bad?
Thank you. I did not plant that question with my grad school classmate, Jared Mills, but thank you for that. Yes, I often get asked the question, why should you care about direct imaging, which I will tell you in a moment. The other thing I wanted to point out that I think is so great about these, about this landscape is that, sort of contrary to our images of what extrasolar planets might look like in 1994, there are whole populations of planets here that look nothing like the planets in our solar system. Maybe the most abundant type of planet in the universe is what we call, kind of optimistically, a super Earth. Probably some of these look like scaled up versions of Earth, but others look like scaled down versions of Neptune. But in our solar system, we have nothing between Earth and Uranus and Neptune. So we don't really know what these planets look like. We also don't know how you can make a Jupiter-like planet at very close separations. And we don't really know how you make a very distant super Jupiter-style planet. And of the three of these, those sound the least interesting. So I do actually often get asked this question by the public, and I want to spend the rest of the time here telling you why you should care about these, why these are the most interesting and important of all of these amazing planets. Yes, what a great audience. Okay. My first reason I like to call visceral satisfaction. Every other method on that plot is an indirect method. But indirect imaging, we actually see the planet, and we see it orbit. So these movies are all courtesy of Jason Wong, Christian Wong. There's another thing about this, which is that I think we should talk about when we talk about it, which is basically that the technology is really impressive. So we have two huge obstacles to overcome in terms of being able to take these images. So the fact that we can detect exoplanets directly is pretty amazing. So let me tell you why that is, and I want to create an analogy here. So the sun is to a lighthouse, as Jupiter is. So Jupiter is, by the way, it has a contrast, which is like the ratio of the brightness of the planet to the star, of 10 to the 9, or 1 in a billion. What do you think a comparably faint thing is relative to a lighthouse? A candle, good guess. Way too faint. Firefly's going to come back. It's really actually quite hard to find the brightness of a lighthouse and also various other things, but as near as I can tell, if you put 10 bioluminescent algae in a clump, you would have something whose ratio relative to a lighthouse is approximately 1 part in 10 to the 9. So this is super great. It would be great if we can do this. We can't. I'm sorry to tell you. What we can do is something 3 orders of magnitude brighter, which is that right now, with current technology, we can image young versions of Jupiter that are still glowing from the leftover heat from their formation process. And that is approximately, and this is much easier, it's just like imaging a firefly next to a lighthouse. I'm not going to get into the angular scales, but those are also hard. I can talk about it during the Q&A if you have questions. Reason number 3, so we have visceral satisfaction. Technologically, it's really cool that we can even do this. And reason number 3, the most important reason, is characterization. So by directly imaging, directly isolating the light from the planet, we can characterize it. We can look at its brightness as a function of the color of light, and it will tell us something about its atmosphere. For example, this planet, 51 Area B, you will see appearing, there's a helpful arrow there to point right to where the planet is. It appears at some wavelengths, it disappears at others. This tells us something about what the atmosphere of the planet is made of. In particular, it tells us that it has a lot of methane in its atmosphere. Does anyone recognize this image? I have it hanging on the wall in my office, and when I sent it to be printed on canvas, the printer got back to me and said, "Are you sure you want me to print this? It looks really bad." But it's one of my favorite pictures in astronomy. What is it? It's the Earth, taken from beyond the orbit of Saturn by one of the Voyager spacecrafts, and that dot there is Earth. So I have grown to love super Jupiters. However, the reason I got into this field was not really to characterize super Jupiters. I was motivated by the idea of taking a picture like this someday of an exoplanet. So what are the prospects for that? Well, on my scale model here, Earth is another factor of 10 fainter than a Jupiter. That's a single bioluminescent alga. I had to look up what the singular of algae was, and it never occurred to me to think about things on that scale. But we will be able to do this with not too distant technology. So what are we doing right now? We're imaging hot young exojupiters that are 1 million times brighter than their star and very closely, very tightly separated from it. In the future, we should be able to improve that by 4 orders of magnitude to get reflected light, Earth-like planets, with not too distant future telescopes, including some of the concepts that were recommended in the US by the most recent decadal survey of astronomy. So I hope in my lifetime we will take an image like this. So this is a simulation of what one of those telescopes might see if there was basically a solar system analog around a very nearby star. Now, why is that interesting? Because if you do the same thing I talked about for that Jupiter mass planet, where we could determine that it had methane in its atmosphere, you could do the same thing for Earth. This is what the Earth's reflected light spectrum looks like. And what's really exciting about it is that there are all kinds of interesting things that we can characterize here that tell us about the Earth's biosphere. So there are things that we call biosignatures in the atmosphere of the Earth, in the reflected light spectrum of the Earth, including things like ozone and water, things that are in disequilibrium, so they're created and destroyed by biological processes. So I'm going to leave that teaser just to say I hope that you all, and certainly I hope that I will someday see one of these for an exoplanet. And maybe I'll throw out some food for thought, which is, our conception of what a planet looked like before 1994 was very Earth-centric. This is obviously also very Earth-centric. So some of, I think, the most interesting things that are going on in astronomy and astrobiology in particular right now are thinking about what life might look like, what an atmosphere that has signatures of life might look like around a planet that looks very different from Earth, that has a different kind of biology or geology happening. So I will leave it there and take some questions. Thank you for your attention. Great, so thank you very much, Kate. You exactly predicted that there will be questions, so I will give the mic back to you to take questions. So just raise your hand, and we'll do questions. Anyone? Yeah, the front.
Yeah, very interesting. It's astonishing how far you can go. But maybe you want to take the leap from just seeing the planet versus also getting a spectrum. You also need to go another step. How much is it a factor 10 again, or is it a factor 100?
So you mean, if I take the light and I don't add it all up just to get a detection, but I spread it out into its component colors, it makes it even harder. Is that what you're asking about?
To make a sensible spectrum.
Yes, it does. So we're doing it now for things on the order of 1 million times fainter than their stars. Low resolution spectra. So I think that the prospects are good that we'll be able to do that for reflected light planets with like the next generation of space telescopes. Other questions? Yes?
You said you know nothing of the super-Earths because we don't have it yet. How could we know something more about those?
So good question. So how could we figure out what super-Earths are? So we do have some information. Super-Earths have all been detected with indirect detection methods, but many of them have been detected with 2 indirect detection methods. One of them is the transiting method, where the planet passes between us on Earth and the star, so it blocks a little bit of the light. It's like an eclipse. So when a planet transits its star, we get a good measurement of its radius. We also detect a lot of those super-Earths, not only with the transit method, but also with a method called radial velocity, which is basically where the orbit of the planet causes the central star to wobble a little bit, sort of kind of moving in and out of the line of sight because of the gravitational influence of the planet. And that allows us to get constraints on the mass. So if you have size and you have mass, you also could get density. And the densities of these planets, these super-Earths, seem to cluster in 2 groups. Things that have densities that look kind of like the terrestrial planets in our solar systems, and things that have densities that look kind of like the ice giants in our solar system. So there is probably a dividing line somewhere in there between things that look like scaled-up versions of Earth and scaled-down versions of Neptune, and it's sort of bearing out in the data. indirect data, but if you combine two methods. Other questions? Yes?
You showed us a bottom-up figure.
Mm-hmm.
And they showed all the planets that we found. I was wondering if you could say, you were saying that the orbit period was 1-to-1 with the distance between the star and the planet.
Yeah.
Can you say that we're the velocity as well?
So could I say how much, like what's the orbital period of some of these?
Yeah.
So it goes all the way up. Some of the directly imaged planets that we're seeing are so distant, it's hard to really even conceive of how they may have formed. They probably didn't form anything like the planets in our solar system. But some of these have, orbital periods, thousands or tens of thousands of years. Other questions? Yeah?
So once we find a planet like the Earth, what are it? What's the next step? Like once we all cover from the bodies, what's the next step for us?
So what do we do after we find an Earth-like planet?
Yeah.
That's a good. I don't know. What do you think? I think I don't know. People talk about things like technosignatures, right? So there are lots of unknowns in whether habitable equals inhabited, for example. So I imagine people will start thinking about stuff like that. Yes?
Is there any relation between the type of the planet and the type of the star they are orbiting?
Oh, that's a great question. So for those who couldn't hear, is there any relationship between the types of planets that we observe and the type of star they're orbiting? And the answer is yes, but we don't really understand all the systematics very well yet. So every survey is targeted usually toward a particular type of star. Certainly we think that the rates, like for example, the most abundant type of star in the universe are these very low mass stars, much lower than the mass of the sun. But they're really hard to see because they're very dim. So we don't have great statistics on the occurrence rates of planets around those, they're called M4s. There are some surveys have been targeted towards sun-like stars, so we have some kind of reasonable constraints, but I don't know, it's a very inhomogeneous sample, so I think the evidence is yes, probably different types of stars make different types of planets, but it's hard to say anything like equivocally about that. Great, well, thank you very much, Kate.